You got it? Yep.
You gave me Braden.
What? Oh, you said Brian. I'm sorry. Will he be here eventually?
I'm not sure.
Should we leave it there? I don't know. I'll take it back for now. Okay, it's still recording, right? Okay, I'll start. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. We thank you that even if we're not awesome, you are awesome, Lord. And we thank you for that, Lord. We thank you that we can have your righteousness instead of our own because you saw fit to come to earth and sacrifice yourself in our place, Lord. And we thank you for that. And just pray that you be with us today. Help us to, again, Lord, understand a little bit more about calculus too, Lord. In your name I pray. Amen. So, guys, I don't know. Are you tired of finding power series for functions? I am. I mean, I'm never tired of it, really. That's a lie. But you know, we have talked about how to find the power series expansion for a function for a long time now. What I want to focus on today, well, I'm going to do a little bit more of that, admittedly. So I want to talk a little bit more about how to manipulate power series, but then I'm hoping, at least the bulk of today, I will focus on like how you can use power series to, say, integrate things, to solve differential equations, to calculate even non-trivial limits in surprising new ways. All right, and also just the raw intuition that the power series idea allows us to simplify functions which are otherwise complicated. So I'm going to try to expose those to those ideas. But first, a little bit more power series calculation. So I think the one thing I haven't shown you guys enough of yet is probably division of power series. Let's do another example like that. Let's find the, so for example, you can find the Maclaurin series for secant x from the cosine series. Right, so what is secant of x is defined to be what? Secant of x is equal to, what is it? 1 over cosine x, right? Now, some of you, if you worked the homework, right, one of the problems was what? I think it was to find the power series for secant, wasn't it? Oh, it wasn't. But you know what happens if you don't pay attention to the homework list and you work problems that weren't assigned? You might have found yourself doing this problem. That's what happened to me. And trust me when I tell you, when I have the solution posted, you can watch it. You can see in the solution, I have calculated the power series for secant from the Taylor expansion. It's rather unpleasant, rather fast, right? Think about differentiating secant. First derivative, secant tangent. Second derivative. Third derivative is also, and this continues. I mean, successive differentiation of secant is a pain. So this is like way better, what I'm about to show you. So what's cosine of x? Well, 1 minus 1/2 x squared plus 1 over 4 factorial, right? X to the 4th and so forth, right? So let's find the Maclaurin series for secant x, just the first few terms. Let's say up to like 4th order or something, all right? So I've got 1 here, right? And I'm dividing 1 cosine into it, so that's 1 minus 1/2 x squared plus 1 over, and let me put the number there. 4 factorial is what? What is it? What is 4 factorial equal to? 24, all right, very good. And so forth, right? Okay, so what's the first thing? I put a 1 here, right? And I do that. What's 1 times this? Well, I get 1 minus 1/2 x squared plus 1 over 24 x to the 4th, right? Then you subtract. That gives me 1/2 x squared minus 1 over 24 x to the 4th, right? All right, so how can I obtain a 1/2 x squared? So I have to think about, I multiply this right here, right? So before I multiplied this times all that to give me this, right? Now I'm thinking about, again, I got to say plus. I want to cancel that out, right? So how do I get that from multiplying something here times this? The leading term should be what? 1/2 x squared, does that make sense? See, because then I have what? 1/2 x squared. And then what's 1/2? That gives me minus 1/4. X to the 4th, and so forth. You take the difference, what do you get? Well, let's see, what's 1/24 plus 1/4? 1/4 is 6/24, right? Yeah, 5/24. X to the 4th plus dot, 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 dot. And then, of course, the next term is, I mean, when we're dividing this particular pattern, it's really easy. And we'll just stop there, all right? So there's the first three non-trivial terms. First three non-trivial terms in the secant, the power series expansion for secant about 0. So therefore, secant of x is equal to 1 plus 1/2 x squared plus 5/24 x cubed, right? Oh, goodness gracious, thank you. My bad. So here's a fun thing you can figure out from this. What are the first and third derivatives of secant evaluated at 0? What's f prime? If f of x is equal to secant of x, what's f prime of 0? What's f the third prime of 0? How do you know that? Very good. Right. So if you're starting to appreciate Taylor's theorem, you start to appreciate that we can read differential information off the power series expansion. Not at all points, right? But at the point of the center, we get information about the derivative and higher derivatives of the function if we already have the Taylor expansion. Okay, guys, how would you calculate the power series expansion for tangent then, if you already had this? Continuing this example. First few terms. Again, successive differentiation of tangent is not that pleasant either, right? So direct application of the of Taylor's series is kind of a drag, right? If you just keep differentiating, it's not. I mean, you could do it. It wouldn't be that hard. It would take you a couple minutes, but I mean, it's nice to have another way. What is tangent? Right? So what can we do? We can say, in other words, we can say sine of x times what? Times secant x, right? Tangent is sine times secant. And we know the Maclaurin expansion for sine x is what? It's x minus 1/6 x cubed plus higher order stuff, right? Oh, plus the fifth. I guess fifth power. I'll go to the fifth power. What is it? Plus 1 over 120 x to the fifth and so forth. We just figured out that secant is 1 plus 1/2 x squared plus 5/24 x to the 4th plus dot. Oh, well, I guess I don't know for sure. I don't know for sure that there's a... Can you see from the calculation already that there's no fifth order term in secant? I think if you think about it for a little bit, you can. a little bit nervous about that. On the other hand, we've just seen that the first and the third derivatives are 0. If this pattern continues, we should also have the fifth derivative 0, right? So let's just agree that it's reasonable to conclude that the next term would be like, I think it's reasonable to conclude there's 0 times x to the fifth, and then plus dot 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 dot. In other words, the next non-trivial term in the secant series is the sixth power, right? Oh, how can we be sure about that? Secant is what? Even, right. Secant's even, so it has an even Maclaurin expansion, so we know this. In fact, from that viewpoint, it's totally unsurprising that the first, third, fifth, and so forth derivatives are all 0, because we know that an even function has an even Maclaurin expansion. See how useful that fact is to actually kind of check yourself on this more complicated calculation? It's really useful. Now we multiply. How do you multiply? Order by order, right? So let's see here. Linear terms, we have what? Looks like the first thing I have is x, right? What's the next order? X squared, except I don't get an x squared because I've got no constant term over here. I've got an x squared, right? But I've got nothing to multiply to get an x squared total, right? So we skip x squared. Oh, by the way, we can expect that too, can't we? Why should we expect that? Tangent is what? Tangent's odd. We should only have non-trivial odd terms in the series expansion, right? That seems like such a trivial comment when I first make it. When you actually start doing examples, though, that is a very powerful observation. Because it halves your work, right? If you allow it to help you. Now this, I get x times 1/2 x squared, so I get a half, right? What else do I have? Minus 1/6. Is there anything else? I think that's it. Then we have x to the fifth. Collect all our x to the fifth terms. So I have 5/24. Then what? Minus 1/12. And then plus 1 over 120. Which is what? Let's see here. I think it's easiest to make this all into 120ths. So this is like 25 minus 10 plus 1 all over 120. Is that right? Do you agree? Disagree? It says 24 times 5 is 120, so that makes that 5 times 5 is 25. This is 10 over 120. That's 1 over 120, so I got 25 minus 10 plus 1, also known as what? 26. 16 over 120, which is what? Four times 4 over what? What did I just say? 5 times 24, right? Which is otherwise known as 4 times 4 over 5 times 6 times 4. So these cancel. We get 4 over 30. Do you guys get 4 over 30? Oh, which we could rewrite as what? Yeah, duh. So, fun fact, f of x equal to tangent x, right? Then the fifth derivative at 0 divided by 5 factorial should be equal to 2 over 15, which means the fifth derivative of tangent evaluated at 0, let's see, 5 factorial is 2 times 15, 2 divided by 15 times 5 times 4 times 3 times 2. In other words, it is 16. It's kind of a sideways application of this calculation, but there it is. Braden? All right. I will take your homework from you now. That'd be good. Go ahead and turn it in. You're that guy? Yeah. It's okay. I wasn't going to forget. I just hadn't gotten to it. I should technically wait until Mr. Tran gets here just to make sure I got everybody's, but he's usually pretty good about giving it to me afterwards. All right. Let's just recap. What are the important power series that you should know, that we all should know and be able to apply? What are our central examples? Of course, and I'm going to write them with u. We have e to the u is 1 plus u plus 1/2 u squared plus dot, 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 right? This we can rewrite as the sum k equals 0 to infinity of u to the k divided by k factorial, right? Next thing, we of course have cos u, which is, so there's basically two important things you should be able to do for each one of these. First of all, you should be able to just kind of without too much mental effort, tell me the first 2 or 3 terms in the series, right? That's one thing. Then, of course, you also need to be able to write down the sigma notation formula because you'd like to be able to do calculations for the whole thing as well. All right. Now, I personally don't look at these as independent things to memorize. I kind of have some organizing principles here, right? Like these 3 things I just wrote down, they go together, right? Like you have the exponential series, then you have the cosh series and the sinh series. If you add the cosh and the sinh series, you get back to the exponential series, right? And so you can see a connection between these 2 things. The coefficients are very much related. And another thing I remember is past cosh and sinh, of course, we have sine and cosine, which are very much the same pattern. What's the difference? We just have this alternating -1 to the k, right? So what are some useful and simple observations we can make about these series that help us remember them correctly and apply them correctly? Well, as we're just remarking, an even function has an even series centered at 0. An odd function has an odd series centered at 0. Don't get carried away with that. If we're not talking about the center being 0, that's no longer true. If you look at sine, the sine function centered at 1, you'll have both even and odd terms. All right? So this even odd business is only good about 0, without further thinking. What else can we add to this list, guys? What's important? Past these basic ones. Yeah, we've derived the log. I don't have that memorized. Derivable things, right? So this I wouldn't say is derivable. This is applicable. 1 over a. This is sort of a meta example because it's everywhere. This is the geometric series, right? And so we use this to do so many different examples, right? That's another one you should really have memorized. In fact, that's probably our penultimate example, right? The ones I have above that, what's the domain? What's the interval of convergence for those? Ooh, I shouldn't do that. It's good. It's candy, not teeth. Okay. Well, there's always a question when you bite on a candy, which is going to win, your tooth or the candy, right? And you hope your tooth wins, otherwise it's bad. Well, this is very boring, intervals of convergence. If you do a ratio test on any one of these things, the ratio test will give you basically absolute value of x divided by like k, or 2k, or 2k plus 1. The thing is, those all go to 0 independent of x. So the interval of convergence for the power series I've written above the line here, the whole real line, every one of these things. This, on the other hand, gets interesting, right? Because down here, we just have to have the absolute value of r less than 1, right? That's what governs the IOC down here, right? So I'm just trying to take a few minutes to kind of recap everything we've done. So let's see, let's look at some specific examples. Something like 1 over 1 minus x, of course, is what? 1 plus x squared, dot, dot, dot. Or you could have something like, x over 1 plus x squared. That would be the sum, k equals 0 to infinity, x times minus x squared to the k, which you can clean up, right? Now, Thomas mentioned a second ago natural log. How in the world do we get the natural log from these? I would just say add, so, if f of x is equal to log x, well, natural log of 1 plus x, let's say, 1 minus x is easier. Then df dx is what? 1 over 1 minus x. And then that's 1 plus x squared plus dot, 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 which then says that log of 1 minus x is x plus 1/2 x squared plus 1/3 x cubed plus dot, dot, dot. Now, technically, I should worry about plus a constant, but does my last expression make sense? Excuse my candy eating. I think you'd rather have me eating candy than coughing like a fiend. Right? Let's see here. You might catch candy eating, but I guess that's okay. It's not really contagious. That's the last thing I've done. Let me underline it in green. This is what I sort of generically refer to as geometric series tricks, where you're given a function, you differentiate it or you integrate it to get to a function which allows geometric series calculation, right? And then you integrate or differentiate to get back where you started, voila, power series expansion. Okay? These are our central go-to tricks. Then what's our fallback? If all this fails, if you can't see pattern matching, if you can't see division of series, multiplication of series, geometric series trick, what do we fall back on past all this? In some sense, it comes before all this. It's section 12.6, Taylor's theorem, right? Which is just take the function, differentiate, plug in the point, and just construct the power series term by term. You can do that, of course. But we try not to because that requires a stupid amount of calculation. And if you want to find a nice formula, you still have to do a bunch of pattern matching, which very few of us are very good at, right? Okay, so so let's do an integral. What if we wanted to do something like integrate, I don't know, How's tech calculate the integral of sine of x cubed dx? Now, just to be clear, this is a question I could not have asked you on test 1. Why? This I won't prove for you, but trust me when I tell you that there is not an elementary function which, when differentiated, gives you back that. In other words, there's no like linear combination of sine, cosine, exponentials, polynomials, logarithms, blah, 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 those things, which if I put it together through some clever combination after making some insane substitution, will give me back that integrand. Like, you can't do it. At least I don't think you can do it. I haven't proved it. I haven't checked it. There's an algorithm to check that. So what do? So what I would typically, the instructions here would typically be what? Find a power series solution to the integral. That's my instructions, okay? And so what I do is very simple. I take the integrand I have and I trade it for the corresponding power series, which is what? Sum k equals 0 to infinity of sine. Oh, I'm an idiot. Uh-oh. Okay, I stopped. Yeah. So we do what? The reason I wrote these in terms of you guys, is to just make it explicit the idea we're plugging in other things than just x into here, right? So it's helpful to think of them in terms of u, because you're going to make a substitution. So like we're going to put u equals to x cubed, right? So I have minus 1 to the k. I can't draw k. Divided by 2k plus 1 factorial, right? And then, let me just, a little bit of side work. I don't want to write all that again. So let me just simplify this over here. If we're looking at x cubed to the what power? To the 2k plus 1. So be careful. We have to multiply exponents. This gives us x to the 6k, right, plus 3. All right? Very simple. And then we use the term-by-term integration theorem, which says that we can integrate term by term. All right? And what do we get? Well, minus 1 to the k divided by 2k plus 1 factorial. And then we have 1 over 6k plus 4 x to the 6k plus 4. And then, of course, you have to add a constant. And there you go. Integrated. You're like, what? Wait a minute. If it's that simple, why did we ever bother to learn all those things we learned at the start of the semester? Like, why do partial fractions? Why do integration by parts? Why do trig substitution? Why do all those things? I can just always use this trick, right? Take the function, convert it to a power series, integrate like a polynomial. You're done. What's the rub? Well, the rub is that the answer is a power series, right? And I suppose that it's just naturally preferred to have something that's not a power series as your answer, right? It's kind of like a weapon of last resort. Now, of course, you can tack onto this things like, suppose you want to calculate the integral from 0 to, say, 0.1 of the sine of x cubed dx, right? That'd be something like what? Now, this formula is great. That's the whole thing. But you can also take a more sort of term-by-term approach, which would be what? What's the first three terms? X cubed minus 1/6 x cubed cubed, which is x to the 9th. plus 1 over 120, x cubed to the 5th power, which is x to the 15th, and so forth. Right, so if I integrate this thing term by term explicitly, I get myself 1/4 x to the 4th minus 1 over 60 x to the 10th plus 1 over 120 times 16. I won't bother to multiply it, x to the 16th plus dot 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 dot, right? Plus a constant, obviously, right? I'll put that at the, we usually put it at the start as a matter of custom here. I don't know, for me, personally, I trust myself more to do the term-by-term integration to actually find the numerical values on the first 3 terms. Of course, these should check, right? If you plug in k equals to 0, what do you get? K equals 0, this whole factor is just 1. 1/4, right? This is x to the 4th. It's exactly this term, right? That's k equals 0 term. So one other thing, I mean, you can check yourself by doing these calculations in 2 different ways is one thing you can do. That should be k equals 0. This should be the k equals 1 term. This should be the k equals 2 term. See, k equals 1, we have a minus. We have a 3 factorial, which is 6. K equals 1, that's a 10. 10 times 6 is 60, minus 1/60th. K equals 1, 6 plus 4 is 10. 10, you know, okay. Okay, all right, so getting back to my numerical problem, we can use that, right? So we've got what, integral, you know, you have 1/4 x to the 4th minus 1/60th x to the 10th plus dot 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 dot, right? You take that, you evaluate from 0 to 0.1, what do you get? You get the series 1/4 times 0.1 to the 4th power, right? Minus 1/60th. Golly, 0.1 to the 10th power, right? So that's an approximation of that integral. How accurate is the approximation? What theorem can we use to say precisely here? What's the error in what I just underlined relative to the actual integral? As you think about the evaluation here, what kind of series do you have? You have an alternating series, right? It's going plus, minus, plus, minus, plus, minus. So the error in what I underlined, this is good to, the error is at most what? You know, 0.1 to the 16th power divided by 120 times 16. And that's by the alternating series estimation theorem, which in some cases, in some sense, is really a special case. I mean, we have the Lagrange's formula for the remainder, right? But before that, we had this theorem. This is my favorite theorem to ask error questions about on tests because it's the most simple error theorem that we have, right? It just says that the error in an alternating series is as much as the next thing we haven't used. In this case, that 16th power of 0.1, which is pretty small, right? So that's a terribly good approximation. It's a very good approximation to this integral. In fact, if I even stopped right at the first term, I'd have a very good approximation. You see that? So we can integrate. That's one of the things we can do, of course, with these power series. What else can we do? Let me talk about one of the problems. This may be one of your homework problems. I don't much care. Uh-oh. Where is... Oh, is the audio working? I forgot to check. Okay, it's a little late. But another example I could show you from section... So basically, we're just in section 12.9 today. I mean, we're never really just in section 12.9, right? 12.9 draws together ideas from pretty much the later half of chapter 12, right? But one interesting problem in 12.9 I should talk to you guys about are these limit problems. I want to talk to you about these. So suppose you're looking at, like, here's number 24. If I've assigned it, I'm sorry. The limit as x goes to 0 of sine x minus x divided by x squared. So how do you, here's a series. The series way of thinking about this is as follows. This is really the limit as x goes to 0, right? And what is sine of x? Sine of x is nothing more than x minus 1/6 x cubed, right? Plus dot, 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 dot. Stuff that's even smaller in x, right? If you're thinking about x going to 0, thinking about very tiny x, right? So these are the two most dominant terms in sine of x at the limit point. And then, of course, I have what? Minus x divided by x squared, right? So what happens? The x's cancel, and you're just left with a limit as x goes to 0 of 1 over x squared times what? Minus 1/6 x cubed plus dot, 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 dot. Right? Terms higher order in x, they're like x to the 5th, x to the 7th, x to the 9th, and so forth, higher order stuff. And you see what you have. You have what? Minus 1/6 x. So the answer is 0. Now, what's the other way you would have done this problem? This is what? This is 0 over 0, right? You could have L'Hopital, like do L'Hopital's rule maybe once or twice, and you also get it. So you're like, well, I could solve that problem before L'Hopital's, right? Fair enough. But I hope you see that this is like a more intuitive way in some sense of understanding what's going on, right? You just replace the function with its power series expansion, and you can ascertain what the limit behavior is. So that's a, there's a lot of these that you can do. Let's see here. Another one we might look at. Let's see here. An integral like this, right? This doesn't even really quite make sense at 0 with the, so the definition of this is that it's sine x over x for x not equal to 0, and it's 1 when x is equal to 0. Now, a function which does that precisely, basically you just, this is what? X minus 1/6 x cubed plus 1 over 120 x to the 5th. So you take that, right? And you divide by x. How does that go? It's just what's just 1, right? Minus 1/6 x squared 1 over 120 x to the 4th plus dot, 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 right? This series, this actually represents, for all x, what I'm about to underline in green. This is exactly, if you look at it, this is, what's the formula for this? It's exactly sine x over x for x not equal to 0, and it's 1 if x is equal to 0. What I've underlined in green is, in fact, you could say it's the function sine x over x with the whole removed. Sine x over x has a hole in the graph at 0. The power series I've underlined in green is the reduced function where that hole has been filled in. It's the continuous extension. Of course, you can integrate that, right? What do you get? You get x, well, we'll say constant, plus x minus what? 3 times 6, 18, right? 5 times 120, 600 is that? Yeah. X to the 5th plus dot 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 dot. There you go. This particular kind of integral appears in optics, for what it's worth. Let's look at another example. A very nice test question, by the way, is something like calculate this integral, definite integral, and give it to a certain approximation, right? That kind of problem is very nice as I think about the test because it simultaneously tests your ability to find power series expansions for functions, right? And also your ability to make simple error estimate arguments. So there's some really nice, I would say, test questions in 12.9. In particular, exercises 31 through 40, really, all of these are nice sort of template test questions. Let's see here. Here's something that's a little bit different. Number 27, we're asked to integrate from 0 to x, natural log of 1 plus t divided by t dt. All right. We're supposed to find a power series. This is number 27. So we're supposed to find a power series solution to this. Now you guys probably remember more than I do. What did we derived the power series for the natural log of 1 plus t the other day. What did we get? Well, 1 plus x. Oh, what's the natural log 1 plus x, the Maclaurin series for that? Do you guys remember? And that's the sum k equals 0. So of course we could also say the natural log of 1 plus u is equal to the sum, let's say j equals 1 to infinity, right? And that would be minus 1 to the j plus 1 over j, u to the j, right? Again, we could derive this with the geometric series trick or by direct application of the Taylor series. Let me not go through that again at the moment. So let's see, we're thinking basically u equals to t, right? So this is the integral from 0 to x of 1 over t times what? Times the power series, let's say j equals 1 to infinity minus 1 to the j plus 1 divided by j, u to the j. Oh, I'm sorry, t, right? Duh. I'm setting u equals to t, so t to the j. Now we can simplify that, right? This is really the integral from 0 to x of the sum j equals 1 to infinity of minus 1 to the j plus 1 divided by j, t to the what? T to the j minus 1. then what do? Well, integrate term by term. I hope you guys don't mind I don't prove that. I mean, there's a proof in the book. You can read it. I don't think it adds much if I prove it. Proof is kind of similar to proofs we've done before, and you guys are tired. You don't want to see another proof. I can sense it. Let's see here. So this is the sum. J equals 1 to infinity minus 1 to the j plus 1 divided by j times j, right? T to the j. That's the antiderivative I would get from just integrating that power series, right? I took j minus 1 plus 1 and then divided by it, right? That's the integration of the t to the j minus 1. And then I have to evaluate that from what? From 0 to x, right? So basically x equals to t equals to x, right? Versus t equals to 0. And what do I get? This is a j squared, yeah? And I got x to the j. Bless you. Kind of interesting. It gives us a weird representation, kind of a weird, I mean, one of the things I see from this example, kind of a fun application. If, just fun fact, I mean, this is just neither here nor there. This is just me counting the roses, let's say. If you calculate the integral from 0 to 1, let's say, for example, then of the natural log of 1 plus t over t, what would that mean? So it's kind of funny. This gives us an integral representation of the sum of the alternating p equals 2 series. So if you want to approximate the sum of the alternating p equals 2 series, you could actually integrate this function numerically, and it would give you, of course, you could just, on the flip side of this, of course, this is what? This is 1 minus 1, what? 1/4 plus 1/9 minus 1/25, and so forth, right? So you could also add these numbers as far as you want to approximate that integral. I don't know, it's kind of interesting. You're like, we have calculators, we don't care. Arr! Strike that comment from the record. It's no use to us. Here. All right, so anyway, the totality of these examples, really, if I have to summarize the method, what's the method? It's really not very sophisticated if you think about what we're doing. Like, the most sophisticated things in terms of calculation we've done, I think, my personal opinion, these geometric series tricks, these are not entirely obvious, right? Like, you're like, oh, well, that's obviously that. Well, okay, if you have this on mind, that's fine, right? But, this sort of thing, the fact that you have to think about, well, if I differentiate it, gets me to something that looks like something that's geometric, and then I integrate to get back, that's a little bit sophisticated, right? And there are higher things down the chain like this. You could, for example, do 1 over 1 minus x quantity squared. We haven't done this one yet. But what if you have this? This is g of x, right? Well, if you take this, the integral of g of x dx is what? Right? If you differentiate that, you get minus 1 over 1 minus x quantity squared times minus 1 by the chain rule. Minus minus gives you plus. And so the integral of 1 over 1 minus x squared is, in fact, 1 over 1 minus x, right? And so then that is what? Well, that's the sum, k equals 0 to infinity, of x to the k. Right? So what did I do? I integrated. And then, so to get g, but g of x, of course, is equal to the derivative with respect to x of the integral of itself, right? That's an identity. So that's d dx of this guy, which is what? K times x to the k minus 1. K equals 1 to infinity. Lo and behold, we have yet another geometric series result. I'll put it over here since I run out of room. So what I've just shown you is that 1 over 1 minus x quantity squared can be rewritten as the sum, k equals 1 to infinity, of k times x to the k minus 1. The examples we've done have gone the other way, right? I give you a function, we differentiate it, power geometric series result, then we integrate back to get the power series, right? What I just did was I took a function, I integrated it to get something that's geometric, power seriesed it, if that's a word, and then undid the integration by differentiation to get that. Let me ask you a hideous question. What if you had 1 over 1 minus x quantity cubed? You can integrate twice, right? So if you integrate and then integrate, that gets you something that's geometric. And then you differentiate and then differentiate again, and that will get you back a power series, which is equal to that. Circle is complete. I personally think this idea is somewhat sophisticated, this idea of successive differentiation or integration to attain something which is geometric. You apply the power series result there, and then you differentiate or integrate to get back where you started. It's an important technique to know about. It is something I will test on. I don't think I need to test on this one per se, right? Like certainly even just one differentiation or one integration is tricky enough. If you look, if you look at my old materials for this course, right, from previous times I've taught it, you'll see in there I actually have a chart where I kind of describe this process. There's like a geometric series chart I have in there somewhere. All right, anyway, I got distracted. My larger point here is just that the way I've been advertising to you that we can calculate with power series is just to do it. You just plug the power series into the limit you're trying to understand. Or you plug the power series into the integral you understand, and then you just basically do polynomial calculation, right? Because we have this term-by-term integration or differentiation. Or in the case of limits, we just replace it with the fewest lower-order terms, and then you're good to go, right? That's not that tricky, really. You guys are just not yet familiar enough with what these are, right? So you want to become familiar with them so that you can apply them, right? What I'm about to show you is a little bit different idea, but it's equally important, but a little bit different. All right, suppose you want to solve y prime prime plus y equals to 0. I'm starting out with this because it's not too bad of an example. The technique I'm about to show you can easily be used to calculate far more complicated examples. You already know the solution to this. What is it? And if this problem appears on the final exam, That is how you should do it, right? Don't make it more complicated. That's how you do it, all right? On the other hand, if on the final exam I was to ask you to solve y prime prime plus x squared y equals to 0, then you couldn't use the technique that I just did, right? Because it's not a differential equations with constant coefficient. It's that more yucky kind. It's a variable coefficient. That problem actually would necessitate the use of the technique I'm about to show you. But I don't want to work that problem because that problem has a messier solution for the moment. I want to start us out with an easy solution to understand, which is this one, okay? So the idea is this. We assume solution has form y is equal to a sum. And I'm going to use n because I'm tired of using k, if that's okay with you guys. N equals 0 to infinity of, let's say, a sub n x to the n. By the way, you also have this freedom. If you're not talking about a problem that's about the nth partial sum, all right? That caveat. I mean, you don't want to see, if you're not talking about the nth partial sum, if you're just talking about like just a full bore series calculation like we've been doing today, you could easily see that we could replace the j's or the k's with n's. Nothing would be lost, right? The reason I have been making a point not to use n is because we use n for the nth partial sum a lot of times, right? And I don't want to confuse you between that and the k. But my n's are just a lot prettier to look at, so let's use n. What's y prime? By the way, the a sub n's, a sub 0, a sub 1, dot, 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 unknown. These are the variables. These are the things that we're trying to pin down. Hopefully that gives us enough flexibility to figure out what the solution is. So what's the derivative? Well, the term-by-term differentiation theorem tells us that this is n equals 1 to infinity of n a sub n x to the n minus 1, right? And what's y prime prime? N equals 2 to infinity, right? Now, if I want this to solve the differential equation, what do I do? Yeah? I do what? What does it mean to solve the differential equation? It means if you plug it into the differential equation, it works, right? So we just plug this up into there. So what we want then is we want y prime prime plus y equals to 0. Now that is actually the sum, n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2, that's the second derivative term, plus the sum, n equals 0 to infinity of a sub n x to the n. I really like showing Calculus 2 students this example because it gives you a sort of different example to try to wrap your mind around. I hope it helps you understand series calculations a little bit more. And it gives us a nice place where we have to change the summation variable in order to add things, right? We can't add apples to oranges. I can't add this to that. This is x to the n, this is x to the n minus 2. I can't just collect these terms together yet because they have dissimilar formats. All right? So what I suggest we do is we re-index. They're both starting at the constant term, right? So it's just a matter of notation. Like, let's change the notation on this one to make it match that one. But we'll make them both match at a new variable. Let's just relabel both of them by j. All right? So, so for this one, we'll let j equal to n minus 2, right? So n is equal to j plus 2. And for this one, we'll be boring. We'll just say